Hello there and welcome back to this video series on control systems. Past couple of classes we have considered armature controlled DC servo motor, studied its dynamics, derived its time constant, and a block diagram is drawn. When we draw the block diagram, we have seen that there is an inherent feedback loop in armature controlled DC servo motor. The video is going to be very little, in which we consider the field control DC servo motor, draw its schematic, and kind of compare FCDC dynamics with AC/DC dynamics, that is field controlled DC servo motor and armature controlled DC servo motor. Try to once again draw the block diagram, a schematic diagram of field control DC servo motor to show the details. This is the armature and armature resistance, and we try to maintain this armature current constant in the case of field control. In the case of armature control, we keep the field current constant, and in the case of field control, we maintain the armature current constant. In the case of this field control DC servo motor, wherein we represent EB as the voltage between A and B, EA as the voltage across X and Y, we are adjusting this EA in such a way that whatever may be the changes in EB, the current IA is constant. Thus, EB is nullified in one way. The action of EB is nullified. Okay. We see that this is the motor shaft with equivalent inertia, equivalent damping, and you have a field winding with RF and LF, wherein we flow this current IF. When current IF flows, magnetic lines of flux cut the conductors here. When this happens, a torque is generated, because of which this angular position of the shaft changes. While all this is happening, an external disturbing torque Td may come onto the motor. This is the situation with field control DC servo motor. We'll try to write the equations for the field circuit. It is straightforward. Drop across the resistor is Rf into If. Drop across the inductor is Lf multiplied by derivative of If. That's the reason why an S term came in. Motor torque is proportional to the field current IF, with the constant of proportionality KFC is the motor constant for field controlled DC servo motor. And for inertia and damping load section, we have this torque Tm should support the disturbing torque, should move the inertia, and should also cause displacement in the damper. So you have Vf divided by this. So this Rf plus Lfs, you take it onto the left hand side. Vf by Rf plus Lfs is If. So that is what this block diagram shows. This current, when multiplied by the motor constant Kfc, gives torque. Motor torque minus disturbing torque divided by this Jfs plus F equivalent gives motor speed. This is straightforward. You see that there is no inherent feedback loop. That inherent loop is coming in armature controlled DC servo motor because of back EMF. The back EMF is nullified here, so you don't see any loop in the block diagram. If you consider this block diagram and try to derive the two transfer functions, this is one transfer function G1 multiplied by Vf. This is another transfer function G2 multiplied by Td. We will again say that inductance is very small and hence can be ignored. We write the equation and manipulate a little bit to get it in the standard form. Time constant term appearing here, 1 plus tau fc into s. This tau fc, we saw that it is J equivalent by F equivalent. If you recall, for armature control, you have J equivalent RA by F equivalent RA plus Km square. We clearly see that this time constant for armature control is less than the time constant for field control. Thus, the armature control DC servo motor settles down very quick as compared to the field control DC servo motor. So a quick comparison of armature control and field control, we see that maintaining IA constant is difficult because this IA constant needs to be maintained in the face of varying back EMF. And back EMF, each time there is a small change in the speed, back EMF changes, and hence EA, that is the applied voltage, has to be varied to maintain IA constant. Similarly, this back EMF kind of acts as an inherent damping. It is trying to resist the change. Such a phenomenon is absent in field control DC servo motor. So, an external damper may be necessary in FCDC motor. This field control DC servo motor requires a big power source to maintain IA is equal to constant, but AC/DC doesn't require that. It may be run through amplifiers. The time constant of field control DC servo motor is more than that of armature control DC servo motor, and hence this armature control DC servo motor settles faster. And this may be because of the inherent closed loop present in the armature controlled DC servo motor. Thus, in summary, we say that dynamic equations for FCDC motor are written. It is seen that there will be no closed loop. Inherent feedback is absent in FCDC. Armature controlled DC servo motor settles faster. And that's all we have for today. Have a great day.